Hello, welcome back to LIVENODING. In this episode, I'll be taking a look at the new Raycast nodes under geometry nodes. So this is the documentations. Basically, Raycast node will kind of intersect two geometry and find the hit points. It's a big node and something you need to try in order to understand. So let's try it with the Susan monkey head. Geometry nodes and search for Raycast. Okay, oops. Okay, this is new feature in latest Blender. It will scroll if you move your nodes to the border. So let's save this very quickly. Raycast. So this node will expect you to have geometry and target geometry. I wonder if the target geometry is supposed to be Suzanne, but let's see. If we have grid, plug this under target geometry, and let's actually observe this using Spreadsheet. Let's name everything here. Hit position, hit normal, hit distance, hit attribute. So we have some results. Is hit, okay. In order to see what's going on, I will also have join geometry and also transform, and the result goes in here. So we're gonna have grid. Okay, and yeah, now we have something if it's hit. The quickest way to test also, if we use delete geometry and then use this is hit over there. Okay, now starting to make sense, kind of. Let me try rotating. So if you imagine the plane as directional or maybe area light, the part where Suzanne being hit by the ray is gonna be deleted. Something like that, the way I understand it. So I just increased the subdivision of Suzanne. We can also use the other subdivision surface, and you might be able to see this better. So if I increase and decrease the plane, I can delete Suzanne based on the angle of the normal. So by default, the mapping is set to interpolated. We can also set it to nearest ray direction vector 1. I think vector 1 is like the z-axis, the normal point, and then we also have ray length. So there's this ray length. So this is the ray being cast, and so if we are rotating the plane, we can see something's happening. I'm kind of curious if we actually switch between Suzanne and the plane. So let's save this again. So what if we switch this geometry and target geometry? Yeah, I don't think it's making sense. I think it's more like the plane is catching the ray from the monkey. So in this case, the attributes that's being output by this Raycast node is used here as delete geometry. I know there's some other that we can use, like hit position. Okay, let's try that. we can use distribute and hit position, HP. So let's not delete our object this time. Point distribute, join geometry. We should have some points. If I increase this 1000 ray, so yeah, we have some hits from that object somehow. This is the ray. So let's try moving this thing around. Yeah, sometimes with the hit doesn't quite make sense. I think it actually, yeah, the ray is kind of casting there, and I thought I can make this really far and go through. Yeah, we can imagine it like an area light. So it does actually goes through the surface. If we go deep into it, okay, anyway, we have hit points that we can use here under point distribute, which is already pretty cool, I think. Point distribute, and we can use this to instance objects. We can also use it to, let's try instance object. So icosphere, make this really small, and then hide it using edge and instance. So I'm instancing the icosphere. We can also use another one, hit, either hit normal or hit distance. Which one is in hit normal? I think because Susan head is not flat, right? There's some kind of normal. If it's exactly parallel, or if there's like an angle, it's like if you're looking at the ball and you can see it's more reflective around some areas. So I think that's related to hit normal. Let's try hit distance. Copy paste. So this is hit distance. Let's multiply that hit distance with attribute vector math. Hit distance multiplied by a vector. So that's the hit distance. And let's move this thing around. Maybe I need to have another point scale here. Maybe I need to invert the hit distance somehow. Or maybe it's a good idea to remap the hit distance. But I think the further away, the bigger the radius. So you get like the edge. Yeah, you kind of left. You can see the edge around Suzanne. Might be easier if we don't use Suzanne and use maybe just like a simple box or cube as geometry that we observe. So this is a basic cube. Size of the cube. This is our objects intersecting the cube. You know, I'm still kind of wondering how this really works. Point scale multiplied by the distance. Yeah. The closer, the further away it's gonna be larger. So we can really use ramp, attribute color ramp. Before we scale, we can, this is like normalizing the value, or attribute map range. The color ramp I think is more like clamping. HD attribute result. This is minimum, maximum. We can invert it. With a clamp. Huh. Could be yeah. But let's see, grid, we can subdivide the grid. Oh, sorry about the noise, it's pretty annoying. We also have the normal HN. Maybe try using HN here. Hit normal. Yeah, hit normal doesn't make sense unless maybe we kind of check the normal and what's the math of it between, if you have two vector and you want to measure the parallel, you might need to use like something like dot products or cross product. I always got that a little bit confused. One of them will generate an attribute anyway. So if we plug this in anyway and we measure the hit normal, HN, and we want to produce HNCP and HNDP. Okay, just made it up. So before we instance, we just gonna output this. Try observing the value. Okay, it becomes point cloud with all this attribute, which is actually pretty cool in itself, because we already distribute some points here and we scale the point. So we have attribute here, and so all the attributes now is becoming just points that we can pass it into point instance. We actually have something new here. We can filter out column. So yeah, I'm not gonna use that for now, but HNDP and HNCP. Let's observe that. Actually, this is an interesting value. HNDP. HNCP. I think HNDP is more interesting. So HNDP we can compare, and we can, with this value, you can see the one that's with a higher value, we can then do something about it. So HNDP for now, I'm just gonna keep that. We're gonna create new value by comparing attribute. So HNDP, we're gonna compare attribute compare. Okay, this HNDP, so greater than a value, HNDP dar as a result. There. So we can have on and off based on that value. And that value can be used to control our instance. hopefully it's not that confusing. Switch, let's use switch. True and false and switch. This, the output of HNDPR is a boolean, so we can use it somehow to trigger a switch, maybe. Or maybe just use HNDPR here. So this is the angle, I believe. Oh, if we keep the visibility here, we can still see the value. Okay. All right. So HNDPR, this is the value it's when it's hit. Become like on and off on the point scale. All right, so let's summarize what's going on, what we have learned today. Okay, so we have the angle of the plane, grid plane, that's coming out here. So that's our plane, which we can translate so the angle will affect our instance and also points. So this is our cube. The cube might not have enough resolution, so let's do subdivide. This is our ray with ray length. I keep the vector here so it's easier. I didn't delete geometry, but I distribute some point based on the hit position. Let's make it 1000. And there's a point scale. That's Raycast. Let's zero this out. Zero the rotation. Point scale, okay, this is attribute vector math. That's multiplying the HD, but then this now have no effects. Cross product, we didn't use cross product. This is the dot product. Yeah, I think I made a mistake somewhere here with it. Yeah, but cross product and dot product is something that we can use at some point, and we can compare it with a attribute compare. For now, the one that makes sense is HD. I think HD hit distance, and so at least we can map this value. So if distance too close, I think it's become really large. Yeah. So it's kind of like we can find the intersection between the two objects. The original cube, we can bring in the original cube, which I deleted. Oh, okay. Okay. We have the original cube that's intersecting with the plane that we can rotate. So there's a ray that's being cast. And if we want to use delete, you can use delete geometry based on is hit IS. It's being cut. It's probably useful for objects that you put on the ground. So you can observe the intersection. Maybe it's also useful for things like a bubble. If you have a glass and you put some liquid bubbles, you can see the intersections between the two. So this is still only one. 001 interpolated nearest, didn't do much. This point scale. Multiply of hit distance being multiplied and being remapped. We can clamp the value. Hit normal we didn't use with cross product and So we just keep this. We can mute it using M. So this geometry being deleted based on the raycast, and I can invert it. So that's, I think, that's what raycast is all about. Maybe in the next video we can see how we can use this, or what is this exactly for. But that's a first look at Raycast Node with Blender 3.0 Alpha. Still work in progress. Maybe there's a bug somewhere there. We can try. I can randomize vector add position. So I'm randomizing the position of this grid. Maybe actually subdivide this grid a little bit. This randomization. So now rotate. You can see the ray is a little bit more accurate now. This is the distance. And ray length. So if we get back to our Suzanne, we can see also Suzanne being cut. Intersect with, at the intersection line we have this large sphere. I don't know what this is actually for, but it's just kind of interesting. We're gonna try and take a look at this again in the near future. But for now, this is pretty much how the nodes kind of work. You can read more about documentation. It doesn't have any example yet. Maybe soon someone will come up with a better video, all right, to explain these nodes. All right, thanks again for tuning in, and I'll see you next time. Thank you. Bye.